of the Korean Women Mathematical Society, to the president of the Korean Mathematical Society, Professor Park, who has been for making my introduction and inviting me. Thank you to you all to being here. It is the first time I came to Korea, so I am very excited, and I am sure that for me will be a very, very nice remembrance when I am thinking about this conference. This is better? And this one doesn't work? This one? Okay. Well, the subject of my talk is about minimal vector fields or Riemannian manifolds, and this is a lecture for not only for geometers, so I am going to explain a little what vector field is and in which sense I am going to look for these vector fields. So let us suppose, just for the beginning, that my manifold is an open subset of Rn, which is D. Just to start, a vector field is usually seen by the flow lines of the vector field, but we need to see not only the lines, the flow lines, but the velocity of in order to see the vector field, we need to see also the velocity at each point. Oh, sorry. The vector field is given in fact, by a map, capital V, a map who represents in fact, the relation between the flow, the line flows, and the map V, capital V, is the following. We know that the tangent to the curve T, the tangent C prime, the derivative, is just the map, the vector field at the point C. I am going to recall that in general, if we have a curve, we can define the energy and we can define the length of the curve. In both cases, the energy is proportional to the norm of the acceleration. That is to say, the second derivative, that in fact is the first derivative of V, of the vector field. So the energy of a curve and is given by the derivative of the vector field. We can call this the energy of the vector field. Sorry. And my question at this, during this lecture, I don't know if probably I can speak without a microphone. If it is probably easier. I don't know if you are going to understand me at the end, but it is. I think I can speak louder. Well, if we have a vector field, for me then a vector field is the flow and the vector field is the map, capital B. The best vector fields in an open set, it is clear when you think the best vector field is just to take a vector and to translate the vector at each point. So there is no doubt that the best vector fields on an open set of Rn are parallel ones. Parallel ones, which is that translate parallelly a unique vector field. But from the point of view of the derivative, let us call us nabla V, the gradient of V, just the derivative, the endomorphism having the... Okay, thank you. The endomorphism nabla V, which is just the endomorphism determined by the Jacobian. So let us, roughly speaking, the derivative. So when the derivative vanishes, our vector field is the best one, that is to say, parallel vector field. The parallel vector field has two properties. So the first one is the norm of the vector field is constant, because I just translate my little vector in each point, And you have the flow lines are straight lines. Straight lines, if you are thinking in the geometric point of view, is that geometries we call geodesics. Straight lines, in general, became then geodesics. So let me propose the following problem, which is more or less what usually is called Gluck and Siller problem. I have a manifold, an abstract one. For those not very used to think in terms of abstract geometry, think about surfaces, that it is more common. Surfaces, subsets, or Rn. Not only on open set, but a surface on Rn. Or if you are geometrists, so think about a manifold. If we have a manifold or a surface, for simplicity, we can also look for vector fields. For instance, if we have, let us write the simplest manifold and a sphere, you can look for vector fields on a sphere. This is just at each point you have a vector, but this vector must be tangent to the manifold. If you think of a surface, at each point the vector should be tangent to the surface. So if you're looking for the best vector fields on a manifold, this is not so easy to say, yes, the best one are those which are parallel, because you think in a surface, which means parallel in a surface. You need a definition. You do not can just put the vector field because probably it is not tangent to the surface. So the best vector fields we can define. We have derivation on manifolds. What is called covariant derivation. And then we can define a vector field, the best vector field, those having vanishing covariant derivative. So now by the visual geometry, we say we can give a nice definition of derivation on a manifold, on a surface, for instance, and we can define parallel vector fields just by the mathematical or say the analytical properties. So we have a geometrical visual property that it means that the derivative is 0, and then we copy this as the property when we have an abstract manifold. And we say vector fields which are parallel. So the problem will be solved, and my conference will be finished if at this point, if every manifold is able to admit a vector field which is parallel. So the best vector field should be parallel ones. But happily for depends how you look the problem, happily not every manifold admits a parallel vector field. And this is a question not only concerning, probably some of you can think, well, locally a manifold is like Rn. This is more or less the idea. Locally a surface is like Rn. But the problem is not only a global problem. It's not a question that locally you can have this processus or taking a vector field and translate it. The question is that not even locally you can do it. Why? Because the curvature of the manifold is an obstruction for having parallel vector fields. So even locally, for instance, if I take a patch in a sphere, only a patch, not the whole sphere, but only a patch of the sphere, even locally, there is not parallel vector field. on Sn. And why? Because if we have a vector field which is parallel in the directions, in the planes, having this vector field, containing this vector field, the curvature must be 0. This is a simple computation. I'm not going to make computations, but you can trust me that if I have a vector field which is parallel, then at each point there will be a direction of 0 curvature. And even it is very well known that the sphere has curvature and constant curvature and different from 0. The curvature, whatever it means, is constant and different. It's different from 0. So the curvature is a local obstruction for the existence of parallel vector fields. So let me say then that in any manifold, in every surface, not flat, having curvature different from 0, it is very natural and not so easy question to answer which are the best vector fields. The best ones, those who will be like parallel, not exactly parallel because they do not exist, the most parallel as possible. Well, this is the main idea, and in the problem of thinking about minimality of vector fields. The first thing I think is on parallel vector fields. I discovered that these vector fields do not exist, and then I try as following Gluck and Ziller to look for the more efficient, well, more likely to parallel. When we think about the sphere, we are looking on spheres because of this example I gave you. For instance, if the manifold is the simplest one, apart from the plane, the simplest one could be spheres. So the first manifold, the simplest one manifold in which the problem has a sense, is the sphere. And Gluck and Ziller were interested exactly in this simplest case, the spheres. So you have a sphere. Oh, sorry, okay, the slides are not. I use Macintosh, so this is not exactly as they're supposed to be. But okay. Okay. So if I think on a sphere, I can think a vector field as a map from the sphere into the tangent bundle, the unit tangent bundle. Why unit? Well, I have said that the parallel vector field has constant norm, and the flow is given by geodesics. So at least I am going to consider only vector fields with constant norm. I say, well, in order for a vector field to be good vector field, the first and simplest idea is that only look for vector fields that have constant norm. If the norm is changing, I suppose the energy is worse. So take norm equal 1, and this is, and they consider this manifold, which is the tangent to the sphere. The tangent to the sphere is very simple. You have your sphere. In order to give a tangent vector to the sphere, you need a point of the sphere and a vector which is orthogonal. So what you need exactly is two vectors which are orthogonal each other. So this is the Stiefel manifold. So an element of the Stiefel manifold of orthogonal two frames, or n+1, is just a vector field, a vector of the sphere. So I look unit vector of the spheres as a Stiefel manifold, and this Stiefel manifold is also, well, can be seen as a quotient of groups, of the orthogonal group. The Stiefel manifold has a natural metric as the quotient of these groups, as a homogeneous metric. So I can see my vector field as a map. Each point to the sphere, each point on the sphere gives me an element of the Stiefel manifold. And I can see my vector field by its image inside this new manifold. So I have a Riemannian manifold, very simple, the sphere, I have this other manifold, which is a manifold algebraically constructed, and I can see my vector field inside this manifold. So my vector field puts the sphere into the Stifel manifold, and the image has a certain volume, n-dimensional volume. So the most similar to parallel vector fields from the point of view of Gluck and Siller problem are those vector fields having less volume. The volume, we can compute the volume, which is the relation between the volume of this image, which is something which I have constructed differently, and the derivative of the vector field. So I have, as at the beginning, I have my geometrical idea, and then I have the analytical expression of this volume. So the volume of this manifold I have constructed into the Stifel manifold. The volume is given by this formula. The square root of the determinant, and this is the covariant derivative. Probably this you can this formula recalls you when you have a graph, the area of a graph. If you look at B being just a map from an open set to R. So it's exactly the same formula, but in that case we have the determinant, and these are not maps, are the covariant derivatives of the vector field, formally the same. So it is clear for the formula that if my vector field is parallel, so if this covariant derivative vanishes, then the volume of the image is exactly the volume of the base. In a certain sense, you can see a vector field like a graph. A vector field is a map from the manifold to the tangent bundle, so it's like a graph. And the volume is like the volume of a graph. So the relation of, this is the, looking at this formula is why Gluck and Siller were thinking about the possibility of looking for best vector fields among those having less volume. For parallel vector fields, if they would exist, the volume will be exactly the same as the volume of the sphere. Well, which are the first candidates they look for? So they think about this problem and they look for the first candidates. The first candidates, you remember perhaps that I have said that a parallel vector field not only have constant norm, but the current, the flow, is given by geodesics. So I can think about the possibility of having on the sphere a flow by geodesics. Geodesics of the spheres, everybody knows. They are just cutting a sphere with a plane. So they are grid circles. So I look for vector fields. The first candidates, probably, they are these vector fields, are called Hopf vector fields. And I am looking for vector fields having as flow grid circles. Well, before I continue, probably there is some topologist or even not necessarily topologist in the room. I must is going to observe that a unit vector field on a sphere only exists if the sphere has dimension odd. So as I am looking for the best unit vector fields, I restrict myself to odd dimensional spheres. When I have one dimensional, if my sphere is odd dimensional, so dimension n is equal, there in the picture, n is equal to n plus 1. So in that case, a very natural vector field, we have the Hopf fibration. My sphere is inside a certain, so my sphere is inside R2 n plus 1. So this is in fact inside C n plus 1. So I use this complex, sorry, n, n, Sn is dimension is 2n plus 1, and this is inside 2 times n plus 1, and this is the complex n plus 1. So there is a natural projection of my sphere of dimension onto the projective complex space. So to each point of the sphere, we have, sorry, to each point I give exactly the complex line passing through this point. Then this is the well-known Hopf vibration, and the fibers of the Hopf vibration are exactly grid circles. And I can take the tangent to this, to the fibers of the Hopf vibration, and this is the Hopf vector field. So it's unit vector field, and well, one can also define it in this way, just using the complex structure, just multiplying by, this is the description, and this is the formula, this is the analytic formula, take a point and just multiply by the E. On the other hand, from the geometrical point of view, for those more interested in geometry, the Hopf vector fields are exactly unit killing vector fields of the sphere. Which is a killing vector field? When you have a vector field on a manifold, but think even in an open set of Rn, the flow of the vector field helps you to move points on the manifold. So in fact, you have the flow of a vector field, and you have some solid there, some part of the manifold. You can move each point by the flow to obtain, moving by the flow, you obtain some other. This is time t equal t0, and this t equal t1. You can move from one time to another, flowing by the vector field. This is a map from an open of the manifold to another open of the manifold, and we call a killing vector field in this map is an isometry. If you have this flow, doesn't disturb very much the form of the shape and the length of curves, etc. So from the geometrical point of view, Hopf vector fields have this property. They flow by isometries. Well, this is more or less technical, but I say that a vector field, you put your base manifold, in that case the sphere, into the stiffer manifold, and but you consider the sphere there, which is topological sphere, but with a metric. So we have into the stiffer manifold, we have your sphere that deforms it. The vector field deforms you, the sphere, and you have not a round sphere. You have a sphere which has been studied previously by Berger, which is called Berger sphere. So it's a sphere in which it is deformed in the direction of the Hopf vector field. So this is some curiosity at the moment. Okay. So let us go back to the problem of the Gilles canceller. The problem is quite old, and the problem, in fact, comes from our result, as always. They have got a result, and the result was the unit vector fields of minimum volume on S3 are exactly Hopf vector fields and no others. So we have a good candidate to call, we are what are going to call best or parallel vector fields on a sphere. Hopf vector fields for S3 are the best one, are the ones having the less volume. So they are not parallel, they are very good. So this is the good news. S3 is very particular case of a sphere. It's an odd-dimensional sphere, but S3 it is inside R4, and R4 is the quaternions, and the quaternionic structure is very relevant for the proof of the Gluck and Siller. Also, the sphere S3 is a Lie group. So it has a structure of manifold, but it's also a structure of group, and both structures are compatible. So it means that, in fact, it's a very special manifold, a very special mathematical object. And Gluck has a student at that period, a PhD student, Sharon Pedersen, and asked her to, well, to do better and to continue to show the next step, that how vector fields were having the less volume for S5. But sometimes your students are not doing exactly what you want them to do. And Sharon Pedersen showed exactly the contrary that Hermann Gluck wanted. So she proved that from n, for n greater than 3, so for S5 and so on, she was able to find other vector fields with less volume than the Hopf vector fields. So although the Hopf vector fields have very nice geometrical properties, are very regular, symmetric, etc., as you always think that vector objects in geometry and in the world should be regular and nice, she was able to find other vector fields that have less volume. So it means that these vector fields, perhaps I am going to, we will go later to this kind of vector fields. So the problem was completely open after these results, because she was able to find vector fields with less volume, but she was not able to show that these vector fields were exactly having the minimum volume. So the problem was completely open. At that moment, I started working more or less after there was some result by David Johnson using the variational approach. So you are looking for those vector fields having the less volume possible. And then you are not able to find it so easily. So let us try the variational approach. So let us look for critical points of the functional. Not minimizers, you look for critical points, and if you are lucky, among all those critical points, you will be able to find the minimum. So the variational approach, so critical points, critical vector fields. This variational approach was just to compute the first and second variation of this functional for general Riemannian manifold. I forget about the moment about these spheres, and I go back to general manifold, and I make a completely different approach. Just looking this as functionals. This is the point of view of functional analysis on manifold, global analysis. This, well, when I tried to this approach, my inspiration was several previous work done by Johnson, and a lot of work done previously with the energy of functional, which is an easier functional, and was, in fact, I have just listed some of the authors, some of them Korean, if I don't. They were working in Pennsylvania with, I don't know if you Hammond were working with Gluck in Pennsylvania, and but I think they came back to Korea, as far as I have seen in the papers. So this subject comes in this group in Pennsylvania. This is Gluck's group. Well, so we changed completely our mind, and we have a problem, and we go up to see the problem from far away. So I start studying critical points of the volume functional. So critical points of the volume functional is exactly equivalent to determine vector fields there are minimal submanifolds. Minimal submanifolds, when you have a submanifold, say a surface into Rn, into R2, R3, so you have those classical and famous minimal submanifolds. Those having, they are not flat, but they are flat in a sense. The curvature is not zero, but perhaps you remember from when you study mathematics, you can define the principal curvatures of a manifold, of a surface. You cut the surface and you look for the directions where the curvature is bigger and where the curvature is the less possible and the big possible. So you can take the product and you get the Gauss curvature, and you can have the sum and divide it by 2, and this is the mean curvature. So minimal are those having zero mean curvature. They are not flat, but in a certain sense, they are almost the most flat as possible. So minimal, we are looking now, we see that we are looking for minimal submanifolds of the unit tangent bundle. If we think of the sphere, will be minimal submanifolds of the Stiefel manifold having the topology of the sphere. This will be our point of view. Well, this is more or less technical, and in order to compute the mean curvature vector field, one has to work, etc. But anyhow, you get some equalities, which is okay. So we have a differential equation. So we remember that there are critical points of the functional. The functional is the integral of the determinant, and after computing, you have the Euler-Lagrange equation of the variational problem. You have a PDE. And this PDE, if you forget about this let us suppose that LV is the identity by the moment. This is just the Laplacian. This is what is called the Raph's Laplacian, second derivatives of the vector field. For those not looking, very used to manifolds, this is a differential operator of order 2 of the kind of the Laplacian, some Laplacian modified. Then one looks, well, okay, this is the second variation, horrible, but, well. In fact, what is important is that after all these things, if you have a unit killing vector field in a manifold with constant curvature, then the vector field is minimal. Well, there is some translation of on the slide. Okay. Unit killing vector field on any manifold of constant curvature, the vector field is minimal. And all the vector fields have exactly the same volume. So a family of vector fields, a family of minimal vector fields, you can find in any manifold of constant curvature just by looking to those vector fields that are killing vector fields. So once we have been during sometimes several years working in these general aspects of the theory, but in order to be able to come back to our problem, there are many possibilities of looking for minimal vector fields in other manifolds, and there are a lot of papers written by many different people on the subject of looking just for minimal vector fields on manifolds. For instance, only groups and any kind of contact matrix, contact manifolds, or etc. But we recall our problem was to understand the best vector fields on the sphere. So we come back to this problem again, and we remember that unit vector fields are minimal, that the ambient manifold has a very particular metric, and there is an open question here. After looking for minimal vector fields on spheres, there's a lot of examples in other manifolds, but we see that the only unit vector fields defined in all the sphere that are minimal are the Hopf vector fields. So up to now, this is an open question if there are other minimal vector fields on the spheres or not. Sometimes I think it's the answer is yes, and sometimes I think the answer is no. But I would prefer that they are the only ones. But I am not able to prove it. And the only thing I know is that many people is working on examples, and there is no example different. They find it on the whole sphere without having critical points, to say. Well, these are Hopf vector fields. This is a picture of a Hopf vector field. Well, it is difficult to look. When you think on the sphere, you always think in the sphere of dimension 2. In order to think on a sphere of dimension 3, it is the best thing is to think on a projection of this sphere. You take one point of this sphere, and you make a projection. In the case of S2, the typical projection, the stereographic projection, you take one point of the sphere and you project onto the plane. If you do the same thing for the 3 sphere, you get all R3 as the image. So this is the stereographic, and you have your Hopf vector field, and you project. So the flow of the vector field, the Hopf vector field, is we can look at this flow inside R3 after a stereographic projection, and so you get these are the circles. By a stereographic projection, a circle is not a grid circle, but at least it continues to be a circle. And they will join all together at the infinity. This line here is in fact a circle, because this is a projection, and a stereographic projection is like this line here. The horizontal line here is in fact a circle. This line, green one, is a circle. So this is our famous Hopf vector field and our best candidate. So it is quite complicated, quite complicated. Well, we've been trying to understand better the problem. So this is a minimal. So Hopf vector fields are minimal vector fields, so they give us minimal submanifolds of the tangent bundle. And on the other hand, one is able to compute second variation. This variational approach has the, the formulas can be complicated, but at the end, it's just computations. So we compute the second variation, and after this computing, I was able with one of my students, that is, to see that vector fields are unstable critical points. So it means that they are critical points of the volume, but they cannot be the minimizers, because the second variation give us that they are not a stable critical points that will be necessary for being the best ones. But our result, very curiously, our result depends on the radius of the sphere. How the radius of the sphere appears? Well, in fact, I don't know. We were just thinking about spheres as glucose and Ziller, and everybody was looking at the sphere with radius 1, of course. Why not? All these spheres are the same. But we were working on this computational aspects, and as I was thinking in a general manifold, I say, well, let us take n, a manifold, not the sphere of radius 1, with any radius. And by making the computation, we can see that things don't work exactly the same for different radius. That there was a difference, at least formal difference, when you change the radius. And this is because the functional is not homogeneous in the radius. When you look at the functional, you don't think geometrically. Geometrically, all the spheres are the same. But analytically, you look at the functional and you see that the functional is not homogeneous. So from this other point of view, say, well, let us put the radius equal r, and let us continue working on that. So we put the radius equal r, not equal 1, just any radius, and we were surprised that we were able to show that Hopf vector fields were not stable, but we need a condition on the radius. This is a condition on the curvature, but the curvature is 1 over r2. Okay, this here. K is the curvature, is 1 over the radius squared. So this condition, K here, encodes the radius. Well, at this moment we were surprised that we were not able to do better. Well, this is technical, just if anyone is interested in. Okay, we were very surprised not to be able to do better. And we were looking for other different proof for the other radius. So you have for several radius, the Hopf vector field were not stable, and for other we were not able to prove anything. So after several years, 5 years in fact, in working with Borrelli from the University of Lyon in France, we were able to show that in fact for a certain radius, if the curvature, if k, if 1 over the radius square is greater than this value, so for instance, there are several values for m equal 2 or so on. So we have shown the following. For several, if you change the radius of this sphere, you have this variable, the radius of this sphere. For certain values, the Hopf vector field is stable. For radius big ones, are big that are 0. And Hopf is not stable, unstable, if the radius is less than or equal a certain one. So the question is, not only we were the processes of showing stability of the functional is different, but the result is different. And this was quite surprising. We take a long time we check it many times because it was not expected at the beginning. What it means? It means that the problem, when you look at the problem and you think of your sphere, the geometry of the sphere being independent of the radius, it is not exactly true. So there's an aspect of the geometry of the sphere where perhaps the radius has an influence. And at least there's a different behavior with respect to the stability of the Hopf vector field. The possibility, if it is a minimal unstable, the vector field, Hopf vector field, can still be the best vector field on the spheres, in spite of the example of Pedersen. Because in fact, for S5, what we see that the Hopf vector field is just the limit for stability. So for radius 1 and dimension 5, just in the radius 1 and dimension 5, Hopf vector field stops to be stable just for this value of the radius, for radius 1. So this is the possibility that the example of Pedersen depends exactly because she was thinking on radius 1. The counterexample to the Gluck-Siller conjecture is completely dependent of the radius. Also, at the beginning, where neither Gluck nor Siller were aware of this question. So, well, this is the stability. This is technical. I am going to. Okay. Okay. So the stability, this point of view, at least we know that they are local minimizers. We are not sure that they are the best, but around a Hopf vector field, they are the best. They are local minimizers because they are stable and critical from this point of view. So we are back here, and so we see that many years ago, after the Gluck-Siller result, the problem is as unknown as at the beginning, because we are looking to the problem. The more deeper we look to the problem, we see more and more different things. Now let me talk a little about the example of Pedersen. So we have not forgotten, but look for, yeah, the eraser is here. We are looking to this variational approach till the moment we get this result, who was very curious, and then I forget for a while of this variational approach, and I go back to the problem. I go back to the sphere to understand. So, and this variational approach is more general for any manifold, for any Riemannian manifold. Of course, I can study the problem in different manifolds, but it is very disappointing if for the sphere I am not able to solve it. So I go back again to the sphere, and I look very deeply which other vector fields one can find on the sphere to be good vector fields. And we look the example of Pedersen. The example of Pedersen was a vector field which is very nice description also. We have a vector field. We have the sphere, and we look for those vector fields who are as near as possible to be parallel. So we have chosen one of the properties. The flow is by geodesic, and we have found the Hopf vector fields, the natural vector fields having geodesics as flow. Another possibility is just to take a unit vector field in one point of the sphere. And you know the sphere, we have said that the equivalent to the straight lines are the grid circles. So we have our sphere, and except for this point here, we can make the flowing by parallel transport along this geodesic of the vector field. We can make the transport of the vector field parallel, and this is completely defined except for one point. So it's a singular vector field. Pedersen example is a singular vector field. It has one singularity. And the singularity is in the, well, if I start in the North Pole, the singularity is in the South. And how looks this singularity? The singularity looks like this kind of singularities. This is in odd dimension. Well, the picture is in dimension 2, but if the dimension in odd dimension is the index of the singularity is 0. Okay. In fact, it was, well, you know that we have a vector field, dynamical system, well, you have a vector field, and then the other the other characteristic of the manifold is related with the index of the singularities. So since I have only one singularity, so the index must be 0. So this is singularity of index 0. So this is a vector field. Then this is constructed by flowing along the geodesics by a parallel transpose, so it's quite parallel in a certain sense, because at least it's parallel in these directions. But I get one singularity. This kind of singularity I can construct, well, okay. The idea of Pedersen was the volume of this vector field, let us call it P. The volume of this vector field is less than the volume of the Hopf one. But now we know that it is true for a sphere of radius 1 and dimension 5. This is true, and we are now, after several years, we are aware that the radius has some importance. But let us fix just the radius 1 case. The volume is less. This kind of singularity of index 0, you can find a smooth vector field that tends to this vector, this one. And such that, this is the proof of Pedersen, you have a family of PT, which is smooth, and the volume tends to the volume of P. This is the reason why she is sure that there are smooth vector fields with less volume than the volume of H. But she has not one single example, this Pedersen vector field, the base vector has one singularity. I know that there are smooth vector fields because this approaching method. We have shown in the same paper with Borelli that this is not.
Linear vector field you are thinking about are non-singular vector fields, or
yeah.
You're only considering non-singular?
No, in fact we are thinking the first problem is if we were able to find one vector field without singularities, like in S3. For S3, the vector field having the less volume is a smooth vector field without singularities. Without. This is a Hopf vector field. So in principle, we try to find a vector field without singularities. But perhaps the solution is that it does not exist. So the idea of Pedersen was, she looked for a vector field with one singularity, less volume than the Hopf, and that can be approached such that there exists a family of smooth vector fields so that the volume tends to the volume of P. So they are, okay, the idea of Pedersen is to show that the infimum of the volume of the spheres for smooth vector fields is the volume of P. And this infimum is not attained, and then there is not a smooth vector field without singularities having the less volume. This was more or less her idea, but she was not able to show the other part, only this part. And probably she was not able to show the other because it's not true, because this is not true that these are the best ones. So by the moment, we were able, Vincent Borelli and myself, we were able to show that the volume, okay, if we change the radius, this K is for curvature, but changing the curvature is changing the radius, it's equivalent. We were able to show that from a certain value of the curvature, this vector field has a volume greater than the volume of the Hopf vector field. So this is true for radius 1. This is true for radius 1 in the proof of Pedersen, but it is not more true for other radius. So if we change the radius of the sphere, this equality is not more true. No. So these Hopf vector fields are, as I have said at the beginning, is the only known examples of minimal vector fields defined on all the sphere, and are for certain values of the curvature up to when the curvature is bigger, so the radius is little. When the radius is very little, they have the less volume among all known vector fields. Well, I don't know how much. 1 minute. Okay. So the conclusion. Well, let us switch. The conclusion is. The conclusion. Well, these are the Pontryagin vector fields. So the conclusion is, at this moment, after 25 years, and we know that we have several candidates. We have this vector fields defined by Pedersen that were as good candidates to have less volume, but in fact they are only for when the radius of the sphere is very, very big. When the radius of the sphere is very little, the best candidates at this moment are Hopf vector fields, but we are not able to show that they are the solutions. When for certain values of there are still these vector fields, the conjecture made by Pedersen, and at this moment, when we were seeing that these vector fields with singularities were very important, and also our problem, as I have said before, our problem, the Gluck-Silver problem, is for smooth vector fields without singularities. And these vector fields with singularities appears in a very natural way. So we start trying to understand the problem in dimension even. And we realize that for dimension 2, so the problem in dimension 3 is solved, is the only dimension where the problem is solved. All dimensions, other dimensions is open. And for dimension 2, the problem were open. So we try to understand the problem in dimension 2 because we knew that vector fields with singularities appears very natural also in the problem, smooth problem. So we have been looking for two-dimension problems, so the sphere as we see it. For two-dimensional problem, we have a very interesting result, for instance, that the tangent to the sphere is just the real projective space. The unit tangent to the sphere is the real projective space that with the round metric, with the round metric. This was an old result by Klingenberg and Sasaki. And well, there was a very nice result also by Berger and Fomenko that Berger and Fomenko has determined who are the minimal submanifolds of the real projective space having less volume. That are exactly the RP2, the real projective planes inside the RP. Okay, say the grid circles, the image of grid circles into the projection. So with these ingredients, we were able to show that this result is going to, well, this just appeared, that among the unit vector fields, technicality with the boundary, of the radius 1 round to sphere, those of this area are Pontryagin, well, this defined by Pedersen, and no others. So the solution for the two-sphere is these vector fields defined by Pedersen as a possible solution for the 5-sphere are not the solution for the 5-sphere, but are the solution for the 2-sphere. And, well, probably it is a moment to stop here.